So let's take a look at our whiteboard for a moment. We've got this concept here of let's just say, two hosts running IPv4. Actually, let's just put three hosts on here. Say two laptops and a router. And we're going to put them all three on the exact same Ethernet broadcast domain, the same Ethernet segment. Okay, so let's give some IPv4 number to these three hosts. Now we know that because these three hosts are on the exact same network domain, part of their IP address in binary from left to right has to represent the group or the network they're a part of. So let's say I give them this. I'm going to have to make this pretty small here to fit this in. So let's say that this guy here is, and I'm going to go ahead and expand this so you can see it a little bit better. So 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. All right, I'm not going to count it all up, but let's just assume that that's 32 bits. I think I'm pretty close there. And then we'll put one more address on this guy right here. I'll do that up at the top so we have room. Okay, so in binary, these are the 32-bit IP addresses I've given to each of these hosts. Now, if we were looking at these addresses from the original implementation of IP back in the late 1960s, early 1970s, the IP code or software that was running on all three of these devices would interpret these addresses the exact same way. It would say the first 8 bits represent our network. That's not 8 bits right there. 1, 2, 3, 4, 5, 6, 7, 8. There we go. 1, 2, 3, 4, 5, 6, 7, 8. So the original implementation of IP would have said, this is the name of our broadcast domain, 10010010. That is our network. And all these other bits are unique patterns, host bits, for each of our hosts. Now I said here the problem with this is, if I take 8 bits, that's the very first pattern I can come up with. Well, we know that's reserved. No network can be the all zeros network. Then we have a whole bunch of combinations, and then the last pattern in binary I can come up with is that. And we know that's also reserved. So everything in between here is 254 combinations. So if I'm limiting myself to the original implementation, here's one combination I've just used, 10010010, which leaves me 253 networks which are remaining. Now that's not very many networks, not very many broadcast domains. Now with classful, if I go into the operating system of all three of these devices, and I change the IP code in a little bit, and I say, okay, you are now classful devices. Look at your IP address in a classful way. Now, instead of just assuming that the first 8 bits represent the network, they don't make that assumption. Oops. See if I can get rid of this box here, if it'll let me. There we go. Now, instead, they do something else first. All these 3 devices independently take a look at the first few bits. And as classful devices, they say, oh, okay, well, the first 2 bits that we have are 1, 0. So that tells me that now my network is the first half of this address, the first 16 bits. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right there. So that is the network address. The first 16 bits. Now, how does that give us more networks? Well, let's focus here just for a moment on the first 8 bits, because remember, we as humans read this address in 4 dotted decimal numbers. So what is the first byte? 1, 2, 3, 4, 1, 2, 3, 4. So that's the first byte right there. Let's go ahead and translate that first of all to a dotted decimal number. So we've got the 128-bit, the 16-bit, which is 144 plus 2. So this is the 146 network, if I did my math correctly. Now in the original days, where the network was just the first byte, the first 8 bits, that means only this broadcast domain could start with 146. There were no other networks available out there that could start with 146. This number was reserved for this wire, this broadcast domain. But now with classful addressing, now that we're saying the first 2 bytes represent the network, that means one wire could be 146.0 dot anything. We could have another wire, another broadcast domain that was 146.1 dot anything. Another wire that's 146.2 dot anything. On and on and on, all the way up to 146.255 dot anything. So that means just for this single number of 146, we have 256 combinations of networks. This one right here, I'm not sure what this is. This is 146 dot, let's see here, let's go ahead and add up the second octet. This is 192 plus 8, that's 204. So everybody on this particular wire recognizes that their group number, their network number, is 146.204. So now with classful addressing, because I'm able to look at more bits of this 32-bit address, that gives me a lot more combinations. So with class B right here, we know that class B starts out with 128. Well, just with 128, I can have a wire that's 128.0. Another wire that's 128.1. I've got 256 combinations of 128. Another 256 combinations of networks that begin with 129. Another 256 combinations of 130. All the way up to 256 combinations of 191. That's what gives us in the class B space over 65,000 unique networks, because we have so many more bits available to us. And for this to work, the system that it's running on, the laptop, the PC, the mainframe, has to be able to look at this address in a classful way. The code has to tell it, the IP code, the software developer has to write the code in such a way that says, look, don't make any assumptions about your address. Instead, look at the first few bits. And whatever the bit pattern is in the first few bits, that will tell you of your 32-bit number how much of it belongs to your group, your network, your broadcast domain. And that's what gave us thousands and thousands and thousands of more networks that were available than when all we had was just our first byte and we couldn't go beyond our first byte. So that's why classful addresses gave us that ability to scale beyond a much larger addressing space.